Chapter 3 deals with basic probability, and in Section 1 of Chapter 3 we get some, shall we say, fundamental definitions about how to do probability. So first off, it's a ratio, it's a fraction, it's a percentage of an outcome occurring divided by the total number of possible outcomes that can occur. For example, the chance of rolling a 5 with a single die is 1 in 6, 1/6, or 16.7%. Those are all the same. An impossible event has a probability of 0. An event that is certain to occur has a probability of 1. So basically, all probabilities need to be between 0 and 1. You cannot have a probability that's greater than 1. An event is any collection of outcomes of a procedure. It can include multiple simple events. A simple event is an outcome that cannot be broken down into simpler components. This may be a single outcome, such as rolling a 5 or a 6 with a single die, or an outcome of rolling a 5 and a 6 with a pair of dice. Getting a 7 or an 11 with a pair of dice is a simple event. Now, there is what's called the fundamental counting rule. Basically, it says for a sequence of two events, A and B, in which A can occur n ways and B can occur m ways, the events together can occur n times n ways. This can extend to more than two events, of course. So, for example, how many ways can the letters A, B, and C be arranged? And you see them listed: ABC, ACB, BAC, BCA, CBA, and CAB. There are 6 ways. Now, how many ways can you arrange the letters A, B, C, and D? Well, what I've shown you here are the first 6, all of which have the letter A first. And then we would have another 6 with the letter B first, another 6 with C, and then the last 6 would be with D first. In other words, we would have 24 different ways that we could arrange A, B, C, and D. Now, a quicker way to count the ways is by using factorial notation. A collection of n different things can be arranged n factorial different ways. And so we should talk a little bit about what does factorial mean. We use the exclamation point for the factorial symbol. Basically, this denotes the product, the multiplication, of decreasing positive integers. So, for example, 3 factorial is 3 times 2 times 1, which equals 6. 4 factorial is 4 times 3 times 2 times 1, which equals 24. Notice how the total for 3 factorial, 6, match the number of ways 3 letters, A, B, and C, can be arranged, and 4 factorial, 24, matches the number of ways 4 letters, A, B, C, and D, can be arranged. It can be thought of this way. With 3 letters to choose from, any of the 3 could be first. But once that choice was made, there are only 2 letters left for the second position. And then once the second letter was chosen, there's only 1 spot left for that third letter. In other words, 3 choices times 2 choices times 1 choice, or 3 times 2 times 1, which is what 3 factorial is, or 6. Now, by the way, on your calculator, I want to get out of the glare here, you have, or at least on this particular calculator, you have what's called a PRB button. Okay? And so, if I hit PRB, please note it says NPR, NCR, and then the third one says factorial. So, for example, if I wanted to do 4 factorial, I would hit the 4, then the PRB button, use my arrows to slide across. Now I have 4 factorial, hit enter, and there's my 24. 5 factorial, 5, PRB, slide across, oops, come back, equals, and so there's 120 ways to arrange 5 different objects. So that's how your calculator can do the factorial function for you, instead of you having to actually multiply 5 times 4 times 3 times 2 times 1. All right, a sample space is the collection of all possible simple events from a procedure. And then there are several what we call types of probability that we're looking at in this first section. There is classical probability, which basically assumes a procedure has n simple events. Each of those events has an equal chance of occurring, and each simple event A can happen S ways. And so what we would write is the probability of A equals S over N. There's that ratio, there's that fraction. The S is how many times we have success in whatever we're looking for. It doesn't actually mean a positive outcome, it just means success for whatever we were wanting to find the probability of. I mean, literally the probability could be how many times does it rain, which you might think of as a negative thing, versus how many times is it sunny. N is the total number of possible occurrences for event A. If the probability of event A is less than 0.001, we call it an unusual event. So right there, that little ratio, just like at the top of the page where we did getting a 5 was 1 out of 6. 1, there's only 1 5 on the dice. 6, there's 6 sides, so 1 out of 6 gives us our probability of success of getting a 5. Then we have what's called a relative frequency, also called empirical approximation of probability. This is based on actual results. For instance, a historical probability, saying something like, last year there were this many deaths due to car accidents, and therefore this year, based on last year, I can make a probability choice about what I expect to happen this year. So it's not really the same as the classical, because the classical is based on the total number of possible outcomes. Well, for something like car crashes, there's no way to actually come up with the total number of possible outcomes. So what you can use is a historical perspective, and we'll see an example of this shortly. And then there is subjective probability, which we'll do the least amount with, but it's based on intuition, educated guesses, and estimates. It's kind of like saying, who do I think would win the Super Bowl? Well, I'm going to start with who do I think are the best teams based on the last few years' worth of seasons. Okay, a couple of things left to go. We have a complement. Basically, if PA, so this is the probability that A will happen, this, with the little bar above the A, is the probability that A won't happen. And it is the complement of this. So again, this and this are called complements. And basically the way it works for rule of complementary events is, you don't have any choices. It either is going to happen or it's not going to happen. And between the two of them, that is all possible outcomes, and therefore it has to equal 1. A probability of 1 that one or the other is going to happen. And then you can rearrange this first equation to find out either the probability that something will happen, 1 subtract the probability that it won't, or the probability that something won't happen, which equals 1 subtract the probability that it will. And that's why they're called complementary events. And then finally, you have odds. Sometimes you may have heard of what are the odds of a team winning, or the odds of a horse in a horse race winning. And basically the odds in favor are the probability of A divided by the probability of not A, while the odds against event A occurring is the probability of not A not occurring, divided by the probability of A. And we'll look at some examples of all of those things. So these are all the basics for Section 1. Let's look at some examples now. So, first off, find the following probabilities. So we want to find out what's the probability of getting a 10 rolling a sum of 10 with a pair of dice. So you're going to roll 2 dice. You know, one may come up a 4, the other one comes up a 6. 4 and 6 is 10. That's the idea. Now, in order to do that, I need to know how many different ways you can get a 10, plus how many different ways you can roll a pair of dice. And so, that's what we have in this table. Okay? Each of these is a combination of the 2 dice. So, they could both be 1s. The first one could be a 2 and the second one a 1. Or, the first one could be a 1 and the second one a 2. Both of these combinations would add to give me 3. 3 ways to get a 4. 1, 3, 3, 1, and of course 2 plus 2. A pair of 2s would give me 4. So this gives you all the possible outcomes of rolling a pair of dice in terms of what face is on the die that's up, and then what their sums would be. Well, if we look for 10s, 4, 6, 6, 4, 5, 5, those are the only 3 combinations that will add up to 10. Altogether, there are 36 possible outcomes. So the probability of getting a 10 is 3 over 36, which is also 1/12. It's also 0.0833 or 8.33%. In general, I prefer the decimals. I don't want you to mess around with having to reduce a fraction. Don't deal with the percent. Just give me the 0.0833. And in general, I want 3 decimal places, not counting any leading zeros. All right, next. What's the probability of getting a face card? In other words, the chance of getting a jack, a queen, or a king from a regular deck of cards. So we've got a deck, and we're going to deal 1 card. What's the chance that it's a face card? Well, there are 4 decks. Each one has a jack, a queen, and a king. So there are 12 total face cards. There are 52 cards in a regular deck of cards, not counting jokers or anything like that. 12 over 52 gives us 0.231. Okay, next. What is the probability of not rolling a 10 with a pair of dice? Well, if there were 3 ways that you could get a 10, then there have to be 33 ways that you don't get a 10. In other words, 3 and 33 have to add up to the entire possibilities of outcomes, which is 36, and that was up here. There are 36 possible outcomes. So 33 over 36 is 0.917. However, we could have also used the rule of complement and say, well, you know, we already found P10 up in part A, so P not 10 has to just be 1 minus P10, 1 minus 0.0833, which gives me, again, that same 0.917. So those are examples of doing classical probabilities. Now, in this next example, we have more of a empirical type. Okay, you have a set of grades. Well, actually, you could look at this still as classical. You have a set of grades, A, B, C's, D's, and F's. You have a frequency distribution, and the question is, what is the probability of not getting a B if you were to select one of these at random? Well, you can add them up, 4 and 16 and 7 and 3, and there are 30 that are not B's. So 30 out of 40 says the chance that one selection was not a B would be 0.75, 3/4, or 75%. Or the probability of not getting a B could have been 1 minus the probability of getting a B. Well, there's only 10 of them. The probability of actually selecting a B would be 10 out of 40. So 1 minus 10 out of 40, we're back to our 30 out of 40. Now you might say, well, which way are you supposed to do it? And in reality, sometimes it's just easier to do the not case, and sometimes it's easier to do it this way. In other words, all I had to do was look at B's and then go 10 out of 40, whereas here I had to do the 4, the 16, the 7, and 3. Now there's only 5 classes, but if I had a lot more classes, that would definitely be a problem. All right, and then what are the odds in favor of rolling a 7 with a pair of dice? Well, again, if we go back to our table, here are all the ways we can get 7. It turns out there's 6 of them. So 6 out of the 36, the odds in favor of getting, or excuse me, the probability of getting a 7 is 1 out of 6. The probability of not getting a 7 has to be the other 30, 30 out of 6. So we do this ratio then, 1/6 divided by 5/6, which is 1/5, or 0.200, 20%. So that's a way of doing the odds. Okay, a couple more examples and then we'll be done with section 1. Okay, this is going with the fundamental counting rule. How many ways can you arrange 5 songs on a playlist? 5 factorial, 5 times 4 times 3 times 2 times 1, which is 120 ways. And as I mentioned, you can do that on your calculator too. So if I go, I'll clear it, 5 PRB, move it over, there's my 5 factorial, hit enter, and there's my 120. A little bit faster way of doing it. Now, this is also part of the fundamental counting rule. I have 12 different shirts, 4 different pairs of pants, and 6 different pairs of shoes. How many outfits, how many different outfits could I possibly wear? Well, it's just going to be the 12 times 4 times 6, which is 288 different ways. All right, these last two deal with those historical approximations. So here we have 5.2 million car crashes in 2009. Maybe that's the last year that they had data from. And then they say there are approximately 136 million cars in the U.S. What is the probability a random car in the U.S. will be in a crash? Well, and again, this is an empirical approximation, but there were 5.2 million crashes. There were 136 million cars. So divide. Please note, if you're curious, the small number has to be on top. You can never have a probability more than 1. So 5.2 divided by 136 says that we have 0.0382. So based on the history of 2009, the chances are just under 4%. And then another one, a weather example. Fresno has had a temperature of 100 degrees or more before the month of May 3 times. This is since 1887. So what is the probability that next April Fresno will have a temperature at or above 100 degrees? So 3 times it's happened. That's in 134 years since 1887. And by the way, if you're thinking it should have been 133, you have to include the 1887 year. So 3 out of 134 gives me 0.0224. So based on history, it's approximately a 2% chance of next April being at least one day above 100 degrees. So there you have a quick intro into probability.